And then let's start. First one should be this. No, not this one. Should be this one. So then I'm going to share screen. Okay. Okay. Yesterday we started to discuss dimensionality reduction. Hold on. Let me put annotation. So we started to discuss dimensionality reduction. And the approach we introduce a new one is a PCA. So principal component analysis. Okay, and it says it is an unsupervised linear transformation. Okay. Dimensionality reduction, you can also apply other approaches. That's like a feature selection. We can also conduct a feature selection. And previously we learned there are a couple ways you can do feature selections. Is it we can through the feature importance. For some reason the pen. Feature importance, the attribute, is it? And then you can sort the feature important, and then you pick the important ones, is it? So that's one way. The other way we can do L1 regularity as a regulation, and because L1 can provide sparse, and it can reduce some weights to zero. And then you can just filter out. So that's about feature selection, is it? But with just feature, it won't deal of the cases. The other way is we call it feature extraction. Feature extraction, is it? And the PCA belongs to feature extraction, is it? Okay, so with PCA, you remember yesterday we discussed as the major idea is what? Who still remember? Because it says it involves some transformation. Is there some transformation? So is PCA still going to use the original feature space or a new feature space? So who still remember that? The concept, PCA. Is it going to use completely new feature space, or it's going to use its original feature space? Who still remembers that concept? PCA is to do what? Is going to do projection. Is it because it's principal component? Is it? What is the principal component? It's what? It's to maximize the variance. Is it? Okay, so it's projected, is it, to some new feature space. But how do you form that new feature space? Is it? You're going to find a new feature axis. Is a new feature axis. And the feature axis is what? Is you do some transformation, is it? With eigenvector. With eigenvalue and eigenvector. Is it? So the eigenvector, the major eigenvectors you derived, is it? It's going to be the new axis. Basically, it's going to be the new features. Is it? That's the principal concept behind the PCA. Is it? And how do you find eigenvalue and eigenvector? It is based on what? Is you use variance matrix. Is it? So we need to form the variance matrix. Is it? And so this is that matrix, and this is the eigenvector. Is it? And the eigenvalue and eigenvector. Is it? So you're trying to find the eigenvalue and the eigenvector. Is it? And the important ones, if you want to reduce the number of features in the new space. Is it? So one advantage for PCA is it's not just be used to reduce feature. Who still remember one of the other functionality it can be used as for what? You remember the example we discussed? Who still remember? PCA can be used to do what? Is compression. Is it? It can be used to you remember we discussed the image, the MNIST data repository, as is a traditional one, as it for the image, for the image, as it after you apply PCA, as it you can have low quality image, is it? But even though it's low quality, but it's still recognizable, is it? So it depends on the computing power, everything, is it, of the other factors you need to think about. Then sometimes in the real world, you may need to have the low quality images to serve the purpose. Is it? So so it can be used for data compression also. Is it data compression? And then you can save space. Is it storage space? Is it? So that's one of the features that you can also use with PCA. Okay, so that's about the review about PCA. So you kind of need to remember, okay, PCA's major functionality is to find a new feature space. New feature space. Is it this new feature space? It may reduce tremendously of your features, original features, is it? But it still can serve the purpose. Okay, so that's, and on the other hand, then it can also be conducted for data compression. Okay, so here it also mentions a couple of applications for PCA. So it can be used for exploratory data analysis. Because when you conduct data analysis, so over here, the examples we saw, majority just have a limited number of features. Is it? The feature space is not big. Is it? But you remember regarding image, then the feature space is very large, as it is even with 28 by 28, is it? And we already got 784 features, is it? So if you use 784 to do training, it's going to, regarding even space, it's going to take a lot, is it? So, but in the real world, when you collected data, then you do analysis, sometimes there may be a lot of noise feature. Noise, is it? And you want to find the major features, is it, within all of the data. So that's what's data analysis. So you can do some exploratory. So it help you to do exploratory work. So PCA is not just used for machine learning or model training. Okay, so you can also use it as some tool to do data analysis. Okay, and like over here says it can also denoise of signals in stock market. It's a noise. It's just some of the features that's not important. But if you include all of the feature, it may impact your analysis. So that's for stock market, is it? And the other major use is that it can also be used for analysis of genome data, okay, and the gene expression levels in the field of bioinformatics, is it? Because with DNA stuff, gene, it's also very comprehensive, is it, features. So if you apply PCA, that may also help a lot. Okay, so this is a review for PCA, the major concept. And what next today, we are going to learn another new approach, okay, for dimensionality reduction, so basically for feature extraction, okay? So the one we just discussed is about PCA as a principal component, is it? So you're going to find the principal component. And today this one is called linear discriminant analysis, so LDA, okay, LDA. And PCA is for unsupervised. Is it? And the previous we learned machine learning general categories, supervised learning, unsupervised learning. Is it? PCA's goal is PCA is working for unsupervised learning. Is it? And its goal is to find the orthogonal component axis. Is it? Of maximum variance, is it? So most spread out ones, is it? The axis, is it? That your variance is going to be spread out along that one, so that it will have the maximum variance, is it? So that's the idea. So the spread out. So here just kind of like you see a lot of data, is it? A lot of data, is it? So regarding this, of course, along the vertical direction, or you see along this tilted direction, the data spread out is not that much compared. We can clearly see along this direction, is it? The data spread out the most. Is it? So PCA's goal is to try to find this kind of component, okay, axis. Is it? So that the variance, so it's spread out the most. Is it? That's PCA. And LDA is different, okay? So it's to find the feature space. It's also new feature space. That's going to optimize class separability. So for classification, optimize the classification. Okay, so what does this mean, the concept behind this, okay? And it's the same thing, it's going to do some transformation technique, use some that's going to reduce the number of feature dimensions, okay, feature space, okay? And I also mentioned it's supervised, okay? Remember this major concepts regarding supervised learning for classification. Okay, so here it shows the diagram, is it? So here what we care about is not that spread out, the most spread out component axis, is it? So here it shows we have two classes, is it? So this is class 1 data, This is the class 2 data. Is it? And you can kind of, and your original feature space may be something like this. That may be x1, x2. Okay, that may be original space. And with the original, you can kind of see it's not easy to separate. Is it? But if we can find the new axis, like over here shows, is it LD1 and LD2, is it? And you can very easily separate them, is it? Very easily separate this two set of data, class 1 versus class 2. But here, there are some conditions for the data that's good for LDA. Okay, one condition is the data along the new component, is it, axis is normally distributed. So your data has the feature of normally distributed, is it? Then it's going to be easy if we apply the LDA, okay, LDA. Because later on we will see for LDA, it kinds of care about the data spread out within classes. So like over here is this one class of data. So it's spread out within these classes. And the data spread out within, so between classes, between different classes, is it? So the data spread out generally, is it, between these two classes, okay? So anyway, you can kind of see there's a difference between the focus that the discussion is about from PCA. The PCA is to find that major axis that data spread out the most. And here it's not. Here is you try to find the axis so that the data separability, is it? You're going to find like this principle or this component, is it, this axis? And we can clearly see this axis is the axis that can separate the data the most obvious. Is it can separate that? Because even, you see, you project off the data, is it, to this axis, and you project the data to the other axis, is it? And it's, you can clearly, it's separable, is it? So that you can clearly do classification, okay? So the goal is try to find this kind of axis, okay? So that's the concept, okay, behind this approach. Okay, then what we need to do theoretically, okay, is about, so we needed to know what, some mean vector. Okay, this mean is for each class we are going to compute. So here D means there are D features. There are D features. Okay, D features. And we have C classes. Okay, so you have C number of classes, each class with D features, is it? Then we are going to form this kind of mean vector for each of the class. Okay, so this is about mean vector for each class, okay, for each class. So that's why you see the dimension is going to be C by D. is it? Because you have C classes. So the number, so over here, is it? So the number of, so for each vector, this mean vector, is it? Its dimension is C, is it? The dimension is C. So over here, is it? So this is so this is mean vector. Okay, the mean vector for what? This is a mean vector for each class, is it? So this is a mean vector for class 1. Class 1, is it? And this is mean vector for class C. Class C, is it? But for each one, is it? It has D features, is it? And then you're going to find the corresponding mean, is it, for each of it, is it, for each of it? Okay, so anyway, this is a mean factor, is it? And then what we care about, is it, like I just discussed, we care about within class scatter matrix, is it? So what does that mean? So this is within each of the class. So SI is for each of the classes, is it? And you are going to find its scattered matrix. And you're going to find each one of it, is it? So that's why over here you have the X, is it, minus the MI. MI we just calculated in the above, is it, for each of the class, is it? Okay, so that's not it. And we also needed to know the between class relationship, is it, between class? So this M is the mean for all samples, okay, just like what we saw last class, is it, for that covariance matrix. The covariance matrix is for all the mean, is it? And over here it's regarding all the mean, and this is each class's mean. Class's mean, is it? And of course, this measures between class scatter matrix, is it? So the concept is you have the group, is it? So the above one discuss within class scatter matrix. Scatter matrix, is it? Matrix. And this one is regarding all of the data's matrix, okay? So same thing, we still needed to find some matrix, okay? And for LDA, then it's going to find what? So you inverse the within class 1, is it, and times the between class 1. So this is a matrix. Then you're going to find the eigenvalue and the eigenvector regarding this matrix. Okay, regarding this matrix. And once you find that eigenvector, then that is our linear discriminant analysis axis. Okay, so that's the way to find it. And here is also the number of discriminant, linear discriminants at most. It's based on the number of classes, okay. Okay, so that's the concept of LDA, okay. And the last one over here we are going to discuss is about kernel PCA. Kernel, and the kernel concept, you remember previously when we learned SVM, is it? We also learned kernel concept, is it? Because it involves the kernel function. Is it? With the kernel function, it can simplify a lot of dot product calculation, is it? Using the features, is it using the features value so that it can simplify, more efficient, is it? And the goal for kernel is to tackle, basically is to convert non-linear problem, is it? By projecting the feature space into new feature space. But here, be careful, okay? The new feature space in this case, because you see for PCA itself, the new feature space, generally speaking, has fewer, as it has fewer features. As it, that's the goal. As it, and the same thing for LDA. As it, that's our goal, to get new feature that has fewer features. And of course, this features is already transformed. Okay, it's not the original features. Okay, so that's the concept. But here, you remember when we discuss SVM, theoretically it's to do linear, is it? Classification, is it? But the idea is quite good. We see, is it, to try to find a maximum margin, is it? Is to maximize the margin. So that's SVM. And but you know, a lot of you remember we discussed, suppose you have like a data distributed in circular way, is it? Then if you just use SVM linear, the original one, we cannot separate that, is it? But if you remember, we do the projection, is it, into three-dimensional, is it? Then it can be separated, is it? Can be separated. Is it? So that's the concept, is it? But when you project it, so originally it's 2D, is it? And then with the kernel function, is it? You project into a 3D space, is it? With a 3D way, and with the new third one, the new third dimension, then it's separable, it's data separable, okay? So you can clearly do classification, that's the concept, is it? That's what the concept of kernel concept is, to tackle non-linear problems, okay? By projecting them onto new feature space. So it's new feature, but be careful, okay, new feature space in this case is a higher dimensionality. So you increase dimensionality, okay, not decrease, okay? And then the class can linear separable. That's the concept of cursor, okay? So your initial feature is D, and then you project into new feature space is K, is it? But this number is greater than the original D, okay, D. So that's the idea. So our goal is to find some transformation function, is it? And like over here shows, is it? So that function, kernel function, is it, creates non-linear combinations of the original features. Is it? Like over here it shows, is it? So the original, you have x1, x2 feature, is it? And you project, you apply them to some way, is it? And you get this new third dimension, is it? This new third dimension Z, what it looks like, it's x1 square, x2 square, and x1 times x2 and the square root, is it? So this is going to be a new feature space, is it? With three, but you see, the idea here is that then you transform to new feature space. Is it? Then in this case, each sample, then you need to conduct, each sample conducts the transformation. Conduct this kind of transformation is going to be computationally too expensive. Is it too expensive? And then you apply the learning algorithm like a gradient descent or whatever. Is it? Then it's going to be too expensive. Is it? Or SVM. Is it? So here it says there. So in machine learning, basically it's mathematics background. If you apply some kernel trick, then we can decrease, okay, decrease that expensive computation, okay, because for PCA, what we care is covariance matrix. Is it? Covariance matrix is what? Is the multiplication of the features, is it? Minus their means, is it? So anyway, so that's covariance features, is it? Just think about it. If you apply this one, original one, is it? And you apply that phi for each x, it's going to be too expensive. Is it? Because you're going to apply to it and then later on you do PCA. Is it? That's too much. So the nice way is says, okay, so we can just directly apply the kernel function to the matrix. Okay, so you use the kernel trick on the matrix itself. Okay, on the matrix. So that saves a lot of expensive computing. Okay, and then you find the eigenvectors. Okay, so that will save a lot of work. So here is that to avoid calculation, the pairwise dot product of samples, is it? We use the kernel function, is the kernel function, so that you can just directly, is it? So instead of, so that it says then there is no need to calculate eigenvectors explicitly. So you just directly apply the kernel function, okay, to, you see, you apply the kernel function to the calculation, okay. So that can save a lot of calculation. So that's the basic idea behind kernel PCA. Okay, so the concept is pretty similar as what we learned before for kernel SVM. Okay, and we are done with discussion with both PCA and LDA. So let's take a look at the summarize. Okay, between both of them. And the LDA is to find feature space that's optimize class separability. Okay, so that's different from PCA. Okay, PCA can also be used for data compression, etc. Okay, and both linear transformation, etc. And for PCA, we can also apply kernel one, we just see, etc. And the PCA, it is mostly used for what? For unsupervised. LDA is for supervised. Okay, so be careful. And there are some other points that we need to pay attention is for LDA, there are some assumptions. The assumption is data is normally distributed. So if data is not normally distributed, then it's not good to use it. Okay, and also it says classes have identical covariance matrix. That's another assumption. Okay, and also features are independent of each other, because if features correlated with each other too much, it's also not good to use LDA. Okay, so those are assumptions. So when you decide to do LDA, you first need to analyze your data is it, to see if your data normally distributed, have identical covariance matrix, and are independent of each other features, is it? So just make sure they meet this assumption, then you can go ahead to use LDA to apply or to achieve the goal for dimensionality reduction, okay? And then for kernel components for nonlinear mapping, is it nonlinear mapping? Okay, because PCA is for linear, is it? But a lot of times the original feature space may not linearly separable, is it? Then in that case, you apply kernel function, is it? And you can project the data to new feature space, okay? And then it's going to be for linear classification, okay? So that's, but the new feature space, be careful, it's a higher dimensionality, okay? Like the example we showed, is it? Okay, so this is regarding the concept, okay? So next, let's take a look at our coding. And you remember yesterday we discussed the MNIST, okay? MNIST is the starting point. It's kind of like hello world for image recognition, is it? So we have some idea about how machine learning can be used to do image handwritten digits, is it? So that's the idea. And for sklearn, you can directly fetch, you can direct download the data, 70,000. It has 70,000 handwritten images. Okay, it's for digit, so 0 to 9, is it? So that's the idea about MNIST, okay? Okay, then let's see. And yesterday we already know this, is it? You download, and the total features I also explained, is it? It's 784, is it? That's because your image is 28 by 28, is it? It's for pixel, is it? For pixel, so you have 28 rows, is it, of pixels, and 28 columns, is it? So you have so many number of pixels, and all of the digits, is it, is composed by the number here between 0 to 255, is it? So that's represent the color code, okay, color code. So that's the idea of this data set, okay, itself. And here, from the original data, is it, you can also kind of display the data, is it? So here it shows the original, okay. And then let's see. So here we also see that, is it, a single data, how it looks like. And for the PCA, is it PCA, a lot of case, you need to specify the percentage of the explained variance, is it? So the explained variance, how many percentage you want to choose to maintain your principal components. Is it? Here it gives the example 95%, is it? Then you can fit the data, is it? And then it shows the number of components, is it? So it decreases from the original 785 to 154, is it? Components. So the feature space, is it, decreased a lot? Is it decreased huge? Is it? So of course that will save a lot of work. And then it also shows with this new 154 components, is it? Then the image will look like what? Is it? You can clearly see the image quality. Is it not as good as the original, but it's still recognizable, is it? And our goal here is just to identify digit, is it? So if this can still identify, then that works, is it? So why do I need that high quality, is it? So then you can what you can do here is you compress the data, is it? Your sample, is it? And then you use compress that to do the training, is it? So that's the idea, okay? So here this diagram shows, is it, based on the number of components, is it? And you can also see when it reach a certain point, is it? This is around like that 154-ish, is it? It already reached 95% of explained variance, is it? So it's already pretty good enough, is it? So good enough, is it? Because later on you can see, with the increase of number of components, your explained variance percentage didn't increase a lot, is it? So it's kind of stable. So this may be an optimized point, is it, for you to pick the number of components, okay? So that's the concept here. Okay, and then we can just skip off those, is it? And here it also shows the diagram, is it, with the decreased number of the components. Is it? You can see even with just 87 components, you can still clearly see, is it, recognize the digit, is it? So it's pretty good, is it? So depends on your application, is it? Maybe your application prefer to use 59 components still recognizable, so why bother not to use it, is it? So that's the idea. And what here we want to see is how we apply PCA and then with the model training, is it? So here we are going to do logistic regression, is it? Logistic regression, okay. So you create logistic regression model, and be careful regarding logistic regression, you can select different solver, okay. So here in this case, the LBFGS, this solver is better than the SIGA one, okay. So that's why over here it pick this solver, and then let's say we create the PCA model. And then we create a PCA. And then you fit the data. Feed data. Is it? With the training image. Is it? And then be careful, okay, you also need to transform data. Transform data. Okay, transform data. And then you can training logistic regression. Is it? So here, your logistic regression training is on what? Is on the transformed data. Is it? Is on transformed data, not original data. Is it? Because for this data, you only have 154 features. Is it? The original, you have 784 features. Is it? So this is for that low quality image. Is it? Image. But you can see, even though it's low quality, it holds out majority of the features importance. Is it? It's just filtered out a lot of noise, maybe. Is it? So that's why we can see this PCA is quite useful. Is it? Okay, and then you do the fit. Is it? And then for testing data, same thing. You also need to, so be careful. Okay. Oh, how can I stop sharing? Sorry. Okay, so what the next is for the testing data, you also need to transform. Okay, and then you can do the prediction, is it, with some selected testing sample, is it? So this is the first image, is it? I'm going to predict the first image, okay, in testing, okay, in testing set. Oh, why it's changing? In testing set, okay, in testing set, and it says, okay, it's going to be 1, is it? And over here, the next is predict 10 images, is it, in the testing set, and here it shows the result. And then if you compare with the original, this is original handwritten digits, written digits, is it? And here we have 10 digits. So basically 10 images, is it? And this is predicted ones, is it? You can see it's match pretty good, is it? It matches pretty good. At least within this batch of testing data, is it match pretty good? Okay, so you can see with the dimensionality reduction with PC, it performs quite good, is it? And you can also measure its accuracy score, is it? In this case, it says can reach 91% almost, is it? And for LDA, it's pretty similar concept, okay, for LDA. For LDA is you need to import the linear discriminant analysis, the LDA, is it, from this discriminant analysis package, okay? Then you specify, okay, the LDA's number of components, is it? And over here, I'm trying to just use that, but this is not a good choice, okay? Because you remember LDA, so this is not a good choice, supposed to be 9, is it? Because LDA, the number of the new axis, is it, should be based on the number of class minus 1 at most, is it? And number of class here, we have 10 digits, is it? So it should be 9, is it? But anyway, here just try to show the concept, is it? So you create LDA model, then you do fit and transform, is it, with the training data, is it? And then after that, you can do logistic regression on the data again, is it, on the data again? And then here we also do some prediction with some testing data, okay? So that's the idea, how to use LDA. You can kind of see it's pretty similar, is it? And then I also tested with the first 10 images from the testing set, is it? And it looks like pretty good for the first 10, is it? And the overall accuracy can reach 87, so it's not as good as PCA, okay? So LDA, because okay, so it's almost done for our class. So LDA in this case is not a good pick, okay, for MNIST, for image recognition, it's not a good pick, okay, because you remember LDA is a condition, the assumption to, but here I'm just trying to show how to use LDA. The condition to use, the assumption to use LDA is the data sample itself has the feature of normal distribution. So if the data normally distributed, then you apply PDA, that will be good, okay? Here is just try to show the concept, okay? Okay, so